He says we can construct an antibody to that. And when I say to that, there's a question. The question is, should we do it to the receptor? So we can eject the antibody. Antibody binds to the receptor and blocks it from binding the ligand. Or should we generate the antibody for the ligand? And it would bind the ligand, preventing the ligand from binding to the receptor. Now, you cannot, with hand waving, figuring out which one you should do, because it depends on all kinds of characteristics of that system. For instance, how fast and how often receptors are internalized into a cell, how often new ligands are formed, how fast they are degraded or excreted by the kidneys, and so on. So you can set up mathematical models, and it looks more complicated than it actually is. So we have our antibody here, and here's our ligand, here's our receptor. Here's the natural binding between ligand and receptor. It forms a complex that's reversible. The ligand is produced, the ligand is excreted, the receptor is produced, the receptor is internalized or degraded. And then we have the various complexes, and we can measure on animal experiments or in vitro sometimes what the affinities are for the different combinations and for the formation of these complexes. And then we can construct time curves. So this the x-axis is time. Here's the percent of ligand that is left after some treatment. Here is the concentration of this complex 3 here as an example. And you can probably not see the details, and it's not important, but it says, depending on what our initial state is, how many ligands we have, how many receptors we have, and what all these affinity rates are, we can get very, very different answers to this question. In some cases, it's better to develop the antibody against the ligand. In other cases, it's better to generate the antibody as a binding to the receptor. And here, for instance, you see that for small L0s, it goes down and it takes a long time. If L0 is 0, the ligand goes down, it's immediately back up. So that's not a good situation. But if you have L0 equals 100, so that's the ligand concentration at the beginning, you can see that this complex stays in the body for a long time. And that might be a problem, might not be a problem, it depends on the situation. We can do real systems. Here is, for instance, a MAP kinase cascade, and there's a lot of modeling going on with MAP kinase cascades and with crosstalk between cascades. And the beauty of mathematical modeling, of course, is that it's essentially unlimited in size. We can deal with hundreds of components. The hard part is to find the right parameters. Well, we can set up models. Here's another example that we dealt with a long time ago. It has to do with purine metabolism. And so this is sort of one of the types of models we set up. And you can see the letters in the boxes. Those are chemical compounds, metabolites. The heavy arrows are chemical reactions, biochemical reactions, usually enzyme catalyzed. And then the thin arrows are activation and inhibitions. And you can see that this is not a trivial thing to analyze. So if I would ask you what happens if we cut this step here, either because of a mutation or because of a drug, what would happen? You would have a hard time saying what would happen. In fact, it is impossible because it depends on all the numerical combination of this. So what can we do with something like that? Well, one of the diseases associated with purine metabolism is too much uric acid. And for the guys, particularly here, for the old guys, and more particularly, gout is one of the hallmarks of this. So you have too much uric acid, you develop gout, and but your life expectancy goes up for unknown reasons, so you can enjoy it longer. And so we can see where does it come from? Why do we have too much uric acid? Well, we can test hypotheses, can explain it. For instance, if you have superactivity of this first enzyme, then the stuff goes out and most of this comes back here. And then we say, okay, here's another one. If you have this enzyme deficiency, that's very bad. It's called Lesch-Nyhan syndrome. People are retarded. Kids usually die before the age of 2. And it's one of the consequences is uric acid accumulation in blood. And then we can say, how can we intervene with the system? Now, If this model were reliable, which I would not trust it to cure my son with this, I mean, we're not at that point, but we will come to that point. And if this type of model would be reliable, we could now test every possible intervention. And, for instance, we could say, well, what happens if we block uric acid production here? Well, it doesn't take a rocket scientist to figure out what happens. You have less of this uric acid if you block the step. So that's not rocket science. This is much harder. Or we can block it up there, and there's a drug that's working here. And then we can ask for side effects. Now, we can only look at side effects within the system. We cannot look at headaches and constipation and those things. But we can see, for instance, if we go with this mechanism here, with this allopurinol, then the uric acid may go up, but the xanthine, which is the last one here, is likely to increase, to accumulate, because it has no way to go. So that might be bad, that might not be so bad. But we can test these types of things, and we could go combinatorically through the whole system and figure out what these systems do. So here's the task of personalized medicine now. The status quo is that medicine is really based on averages, and the averages come either from epidemiology or from animal experiments, usually from combination of the two. And the task for personalized medicine is to progress from average input-output relationships to a deeper understanding of disease processes in individuals. And the challenges, two challenges, are to get data and then to analyze them. And those are our challenges. Your challenges would be, well, how do we deliver a corrective action? And I have not mentioned that here. So the analogy is like engineering, that if you really understand how a machine is put together, you don't have to take every single machine apart. You understand the principles, and even though a clockmaker had never seen a particular clock, he or she would know what the problem is if there's a cog missing or so. So we need to understand the principles behind these types of systems before we can really have targeted corrective actions. So the modeling approaches that can help us in this are sort of various sophistication, let's say. And here's sort of the time axis. We can look at biomarker associations, biomarker networks, and I'll go through that. And then parameter variation in disease models, and then the long-term development of disease. And I want to talk about something new that's called disease simplexes. So with biomarker modeling, in some cases, it's easy. So we have one SNP here in the hemoglobin gene, and we get sickle cell anemia. That is easy to diagnose. It's not an easy disease, but it's easy to diagnose. Things like the Oncotype DX test that looks at 21 genes. So that's a whole combination, and those two have to do with remission of breast cancer. So what we really want to do is go into hierarchical networks of biomarkers. That's where it has to go. So we want to look at disease. We want to find out what biomarkers are, and there are very, very many biomarkers, things that are associated with disease right now. That is not sufficient. So we need to look at some that may be important, maybe not, we don't know. But then we want to look what biomarkers give us some indication that 10 years later you may have a biomarker that is really indicative of the disease. And you can see how this goes. So you would like to look at apparently healthy people and see what their status is, follow their trajectory over time, and see whether the trajectory is going the right direction or the wrong direction. And I'll come back to that in a little bit. And Georgia Tech is working with Emory on a predictive health institute, and that's what they would like to do conceptually. They are starting analyzing lots of biomarkers in healthy people, young people and old people who are apparently healthy, you never know, and then they would follow them for the next 20 years or so, or 50 years, or however long they can afford it, and then develop trajectories that lead from health to disease, metabolic disease, neurodegenerative disease, cardiovascular disease, those things. So the real crux is that we get into dynamic disease modeling, and I showed you the purine metabolism example. That is sort of an example. And now we need to go into the personalization of those types of models. How do we do that?